All I'd handed out the parent functions handout, and we went through this list of 8 parent functions, and the whole point of that was to familiarize you with what these basic graphs look like, the most basic versions of these 8 different kinds of functions, what their graphs look like. We had stuff on there like absolute value, parent function, quadratic function, parent function, cube root, square root, logarithms, all kinds of stuff. Are we going to use all those this year? Probably not. We'll get through most of them, but probably not all of them. But I want you to be familiar with them because over a kind of a combination of this year and next year, you're going to look at all of those for sure. Okay? This unit, we're going to look at 2 of them in particular, and that's really it. We're going to look at absolute value graphs and quadratic graphs. Okay? So let's start with the easier of the 2, which is an absolute value graph. And what we want to be able to do with this graph and eventually with all of these parent graphs is we want to know how we can take the simplest version of that kind of a graph and make it more complex. Right? There's some things we can do to it. So let's just start off with an absolute value graph. Now, think back here. You got to kind of go back a couple weeks. What's the shape of an absolute value parent graph? It's a V. Good, it's a V. Where's the vertex of the V? 0, 0. So it's at the origin. And then if I go over 1 to the right from the vertex, what do I do vertically? Go up 1. If I go over 2, I go up 2, etc. And so that's the right leg of my absolute value graph. Now how can I kind of cheat here and get the left leg real easily? Symmetry. Yeah, I can reflect this over black. We'll call this the axis of symmetry. So that's the folding line, right, or the reflecting line. If I reflect it or fold it over that line, each of these points that I used is going to have a mirror image point over here. And when I connect those, I get the other leg. And it's got that folding symmetry, that line symmetry or mirror symmetry. They all mean the same thing. Okay, so now there's our parent graph. That's the simplest absolute value graph we can make. What could we do to that? We talked about some things we could do to that to transform it. Like, what's one thing we could do to this graph?
I don't remember what it's called, but it's like reflecting it like on the x-axis.
Okay, so we could reflect it. We could flip it over so it opens down instead of opening up.
Yeah.
Agreed? So the V could open down instead of up. There's one thing. What else could we do? We could dilate it. We could vertically dilate it, so we could stretch it vertically or compress it vertically, right? And then what else can we do with our V? Translate it, meaning slide it. I can slide it horizontally or I can slide it vertically. Those are the 4 things I can do. And I can do those 4 things by just introducing values for 3 parameters, 3 numbers. By choosing those 3 numbers, we'll dial in any of the infinite possible absolute value graphs that we could graph in the XY plane. Okay? So now, if we're starting with the parent graph and we're going to create this more complicated graph, call it f of x, what are the 3 parameters that allow us to do all that fancy stuff? Usually we'll assign them some letters, but the letters really just stand for numbers.
A, H, A.
There you go. A, H, and K. Where does the A always go?
In front of the.
You're right. Good. So it's always going to be in front of the function, okay? It's always multiplied by the function. So remember, what we called this was our vertical dilation factor. Let's make sure that makes sense, right? Vertical, okay, vertical up and down. Dilation means we're stretching or compressing. And factor in math. What's a factor in math? Something that's being what? Multiplied. Yeah. Right? So this is something that's going to be multiplied by the function, which determines if it's stretched or compressed, or what happens if A is negative.
It does. What does it?
You told me earlier.
Does it flip it on the x?
It flips it. So that's what flips it, so it opens down versus up. Okay. Now, do we have to think of those as 2 separate things? Not really. The way that we're going to use the vertical dilation factor, whether it's positive or negative, we think of it in the same way. And so you don't really even have to distinguish those 2 things. A lot of times we do, but we'll see that they're essentially the same thing. What else have we got? H and K. Where does the H go? In the absolute value. So H is always going to be the number that's being subtracted from x inside the function. Okay, and that's what we associate with a horizontal translation. And then k, where's that one go? On the outside. That's the number that we're adding outside of the function. And that's our vertical translation. Okay, but we can be tricky with this. If we know that the vertex always starts off at the origin with our parent graph, so you tell me what are the coordinates going to be? Where's it going to end up if I slide this thing h horizontally and k vertically? What are the coordinates of the vertex going to be?
Whatever it is.
Yeah, h and k, aren't they? Right? Because h is telling us how far we're sliding the x coordinate from 0, and k tells us how far we're sliding the y coordinate from 0, right? So there's an easier way to think about this. We can just think about the vertex as having the coordinates h, k, right? Okay, so then I just want to go through some sample problems from the assignment, and that's really it. There's really only 3 different kinds of problems that you're going to see on this assignment, eventually on the test. It's pretty simple. And you're just picking out, you're just inspecting the function to determine, okay, what are the values of a, h, and k? And you know by where they show up in the function. So what's a? 1/5. We know that because it's what's being multiplied outside by the function. What's k? K.
Okay.
-4. And you guys already, that's the one I was saving the hardest for the last, but you already got it. What's h? -10. Good. And that's the one that's tricky because remember, it's what's being subtracted from x, and so it's always going to be the opposite of whatever that operation is inside the function, right? Okay, so then the next thing is we want to practice graphing this, and that's really what most of this assignment is about. Is how can we come up with a graph of a complex absolute value function, one that's been transformed from the parent graph. So all we really have to do here is we just have to ask ourselves, okay, what are the values by just inspecting the functions, like we did in that last one? What are the values of a and h and k? And if I know what those 3 values are, I can always turn that into a graph pretty easily. Okay? So what's a?
1,
Okay, which one is it?
it's the thing in front of
You're right. So there's a is what shows up, it's what's being multiplied out front, but if there's nothing there,
the, be 1.
it's going to be a 1. Because it's being multiplied, it's got to be a 1. Okay? So a is 1. Right? What is h? -4, good. And k is? Okay, so then we can graph this pretty easily. If I'm going to graph an absolute value function, it's a pretty simple shape. What's the most important point for making my graph?
The origin.
What do I call it? The vertex. I just need to know where the vertex is, and from there, I've got to find the shape based on the vertical dilation factor. Okay? Well, what are the coordinates of the vertex? -4, -7. So we go -4, -7. So there's my vertex, right? Because those are the values of h and k. So now we got to figure out what's the shape of this thing going to be. Remember, the purpose of a, the whole point of a, the vertical dilation factor, is that's telling us what are we going to do to the regular parent heights of the function, right? If a is bigger than 1, I'm going to multiply the regular heights of the function by something bigger than 1 and make the heights bigger, which will stretch it out, right? If a is a fraction that's less than 1, like 1/2, for example, then I'm going to multiply all of the normal heights of the points on the graph by 1/2, and that's going to make them smaller values, so it's going to squish the y values down, isn't it? Right? Okay, so for this one, we always want to compare it to the size of to the regular parent graph. For my parent graph, if I go 1 to the right, what's the height going to be? Everybody agree? If I go over 1 to the right, the height is going to be 1. And so if I want to find out what the dilated height is, and this is going to be a pretty boring one in this case, I'm just gonna multiply the regular heights, in this case, 1, by A. Well, what's 1 times 1? 1, right? So we end up with A times my height equals 1. And so there it goes. Nothing changed. It made sense, right? If I multiply, if A is 1, I'm not multiplying the heights by anything other than 1, which doesn't change their value. And so when A is 1, we always know that the shape of the V is normal. It's a regular absolute value shape. The only thing that's changed here is that the vertex is not at the origin anymore. It's been translated horizontally and vertically, but the shape stays the same. Okay? Make sense? Let's look at another example. Okay, take a second and see if you can identify the values of A and H and K here. So what's the value of A this time? Okay, -1, because if I have a negative out front, that's our shorthand for -1, right? So you can already tell me probably what's going to happen to the shape of this thing. What's it going to do? It's going to go down instead of up. Instead of going over 1 and up 1, it's going to be the same. It hasn't been stretched, but it has been reflected. So it'll go over 1 and down 1, wouldn't it? And what about the values of H and K? Yeah, now H is the number that's being subtracted from X. If nothing is there, what would that be? It's got to be a 0, right? If it's a number that's added or subtracted and it doesn't show up, then that's an implied 0, right? So 0, and then what's K? 0.7, right? So our vertex is going to be there at 0.7. And now normally we'd go, if I go over by 1, I would normally go up by 1. But now we've got to multiply the normal height times A. Well, what's -1 times 1? -1. So now instead of going up by 1, my normal parent graph point would be there. When I go over by 1, I'm going to go down. I'm going to go up by -1, which is just down by 1, isn't it? And so there's my point. And then if I reflect this thing over my axis of symmetry, it's just a downward opening V. Okay? How about that? What's A? Okay. And H and K are what? Okay, so the vertex is at -6, -4. All right, and now normally we would go, if I go over to the right by 1, we associate that with a height of 1 for our regular parent graph. So the parent height is 1 at that point, and I've got to multiply that by A to find the dilated height. So -2 times +1 is what? Okay, so -2. Instead, I'm going to go up by -2. When I go to the right by 1, I'm going up by -2, which is down 2. And there's the point I need to graph the V. There's my vertex. I get a reflected point on the other side. Does that one make sense? Seem logical? Okay, we know that the vertex is here. And A is, the 2 means it's been stretched, so it's twice as tall as normal. And the negative means it's been flipped. Okay? About one with a fraction. What's A this time? Okay. And what's H? Okay. So -5, +7. There's our vertex. And now we've got to multiply the normal heights by -1/3, but we want to be smart about the point that we pick on our parent graph. We got a bunch of choices, don't we? We could go over 1 and up 1. I could go over 2 and up 2, over 3 and up 3, over 4 and up 4. Now, which of those heights would be a convenient one to multiply by -1/3? Because that's A. 3 would, wouldn't it? So here's the one we'd pick. We pick the one where we go over by 3, which means at that point, the height is +3. So if we multiply A, our vertical dilation factor, times the height, the regular height, what's -1/3 times 3? -1, there we go. So that means we're going to rise by -1. So there's the other point. Does that one make sense? Does that fit the A? So the 1/3 part is telling us it's been compressed because it's less than 1, and the negative part means it's been flipped. Okay? All right? Okay, last one. The very last kind of question I'm going to ask you to do on the assignment is just reverse your thinking. I think these are easier than the other ones. This time all we've got to do is, based on the graph that you're given, you want to figure out what are the values of A, H, and K, and then I'm just going to plug those into my template, right? All I've got to do, once I know what those values are, once I know what A and H and K are, I just plug those values in to write the transformed function. Well, H and K are pretty easy. What are the values of H and K? -2, -5. Okay, so we know and we can see that because those are the coordinates of the vertex, right? Now what about A? So we gotta ask ourselves, in this case here, to get from the vertex to the next convenient point on the graph, how far have I moved horizontally? To get from there to there, I went over 1. Okay, so I went over by 1. Now normally if I go over by 1, I do what? Normally I'd go up by 1. Okay, and so that's where my point would normally be. What are we doing here? Well, in this case, we're going up by -5 or down by 5, right? Yeah. So then if we want to figure out what A is, remember, all A is doing is the dilation factor is telling us what are we multiplying the parent heights by to get our stretched heights, right? So we had a height here of 1. So 1 times A, which we don't know yet, right, has to equal -5, right? Doesn't that make sense? I'm multiplying the parent height by the vertical dilation factor to get the stretched or the dilated height. So I'll solve for A. Well, -5, right? So A is -5. If I just plug that stuff in, then what do I get? F of x equals A times the absolute value of x minus what? X minus -2, which makes it a +2, good. And then -5. And that's what that graph is. Okay,
Nice.
make sense?
Yeah.
Okay, that was a quick review. I made it quick because I know a lot of you guys are already done with this assignment. You can have the rest of the period, well, that's pretty good. You have the rest of the period to work on finishing up 3.2 practice 1. That's what this assignment is. Make sure you can do, make sure you if you haven't started it yet, try some from all different parts of the assignment. Skip around a little bit so you can make sure you can do all different kinds of problems on the assignment. Okay? Have at it. Get questions answered if you have any.